Hey there, universe nerds. You probably think black holes are eternal, bottomless pits from which nothing ever escapes. But what if I told you they actually fade away? That even the darkest, most powerful objects in the universe slowly evaporate into nothing? That's not science fiction. It's Hawking radiation, one of the most astonishing discoveries in modern physics, proposed by the brilliant Stephen Hawking in 1974. It changed how we understand black holes, and maybe how we understand the universe itself. To grasp Hawking radiation, we have to start with something that sounds impossible: the idea that empty space isn't really empty. In quantum physics, the vacuum is alive with activity, tiny fluctuations where pairs of particles and antiparticles constantly pop in and out of existence. These virtual particles appear for a fraction of a second, then annihilate each other and disappear again. Normally, this happens everywhere with no lasting effect. But near a black hole's event horizon, something extraordinary can happen. Imagine one of those virtual pairs appearing right at the edge of a black hole. One particle falls inside the event horizon, while the other escapes before they can annihilate. To an outside observer, it looks as though the escaping particle was emitted by the black hole itself. Over time, this process repeats, and the black hole slowly loses mass as it emits radiation. That radiation, faint, steady, and unstoppable, is what we call Hawking radiation. It means black holes aren't perfectly black after all. They glow, ever so slightly, with quantum fire. The effect is tiny, almost unimaginably so. For a black hole the mass of the Sun, the radiation would be far weaker than the faintest background light in space. But for smaller black holes, the process speeds up dramatically. The smaller the black hole, the hotter and faster it evaporates. A black hole the size of a mountain would glow fiercely, releasing bursts of energy and particles until it finally vanished in a brilliant explosion. These hypothetical micro-black holes might have formed in the early universe, and if any still exist, they could be evaporating right now, leaving faint flashes of gamma rays across the cosmos. When Hawking first proposed this idea, it shocked the scientific world. Before him, black holes were seen as pure one-way traps, objects that could only grow larger. But Hawking's insight merged quantum mechanics and general relativity, showing that even black holes obey the laws of thermodynamics. They have temperature, entropy, and energy, meaning they can gain and lose heat just like ordinary systems. It was the first real bridge between the two great frameworks of physics, the quantum and the cosmic. The concept also led to one of the biggest puzzles in modern science, the black hole information paradox. If black holes evaporate completely, what happens to the information about the matter that fell into them? Quantum physics says information can't be destroyed, but if a black hole disappears, where does that information go? Does it get encoded in the Hawking radiation somehow? Or does it escape through some hidden quantum process at the event horizon? Physicists have been wrestling with that question for decades, and it's still unsolved. Some think the answer may require a full theory of quantum gravity, the ultimate unification of physics that Hawking himself spent his life searching for. In a strange way, Hawking radiation gives black holes a kind of life cycle. They're born from collapsing stars, live by swallowing matter, and die slowly through evaporation. The larger they are, the longer they live. A supermassive black hole could take 10 to the 67th years or more to evaporate completely. That's long after every star, planet, and even atom in the universe has decayed. The last light in the cosmos might not come from stars or galaxies, but from the final whispers of evaporating black holes, fading into the dark. Some theorists even wonder if the final moment of a black hole's evaporation could leave behind something exotic, a Planck-scale remnant, a tiny, stable particle containing all the information the black hole ever held. If that's true, those remnants might still exist everywhere, tiny fossils of long-dead black holes. Others think the final burst of Hawking radiation could release everything that fell in, resolving the information paradox in one brilliant flash. Either way, the end of a black hole isn't silence, it's transformation. And there's something deeply poetic about that, isn't it? The idea that even black holes, the symbols of cosmic death, are part of a cycle. They don't last forever. They give back their energy, atom by atom, photon by photon, until all that remains is the faint glow of quantum noise. Hawking radiation reminds us that the universe, for all its violence and gravity, is also balanced. Everything that falls in eventually comes out. Every darkness eventually fades. So what is Hawking radiation? It's the whisper of a dying black hole, the quantum sigh of gravity itself. It's proof that even the most mysterious forces in the universe follow elegant universal laws. And it's Stephen Hawking's gift to science, a reminder that even at the edge of a black hole, where everything seems lost, the universe still finds a way to let light escape.